yeah, so our second speaker is Gregor Seiler, who's also at IBM Research Europe, Zurich. Yeah, so he will talk about the actual constructions that how to construct those multiplicative and unstructured proofs that I mentioned in the previous talk. So thank you. Go ahead, Gregor.
Yeah, thanks for the introduction. Yeah, so as we know, this is about basically techniques we have developed in maybe the last 6 months or so. And in particular, this is joint work with Thomas, Mohammed, Vadim, and Khan. And yeah, so maybe I should also say, so you have already said a lot of things that I need, but this talk is still going to be somewhat self-contained. So I will basically reiterate some of the things, and I hope this is useful because yeah, there will be slightly different notation, and I will somewhat often introduce a slightly different point of view, and then it's good to have this in mind for the later talk or later part of the talk. Okay, so let's, no, this doesn't work. Yeah. Let me just start very lightly and somehow set the stage again, what we're interested in. So basically what we tried to do, or what we're trying to do, is build zero-knowledge proofs as they are needed for lattice-based constructions of practical schemes. And maybe the most important practical schemes which really have zero-knowledge proofs at their core are maybe privacy-preserving protocols. And one particular example of this is group signatures. And if one builds these schemes with lattice problems, then basically the thing one has to prove always is of the form of this equation on the slide. So you really have to just prove a linear equation over ZQ, which or basically where the solution is short. This is very important, otherwise, of course, the problem wouldn't be very interesting. And short for this talk always means that the coefficients of S there, as Vadim has said, they are basically ternary. So they're in -1, 0, and 1. Okay, so so if we are looking at lattice-based schemes, then of course it is somewhat natural to also try to build the zero-knowledge proofs that we need with lattice techniques. So this is maybe elegant, but it also has practical advantages, namely it leads to simple implementations if we don't have something which is completely different. So the proof system will basically be able to reuse most of the computational things that are also needed for the underlying schemes. And maybe from a more theoretical point of view, it is also interesting because we won't introduce any new hardness assumptions. But as Vadim has also said, there are actually very efficient PCP type, somewhat generic proof systems whose security only really rests on the security of hash functions. So the second point doesn't really apply to them. And yeah, so in practice, this means if it turns out that these PCP type systems are maybe a factor of 10 or a factor maybe even 2 orders of magnitude more efficient than what we can build with lattices, then it gets really hard to argue why we're not using them. So this we always have to keep in mind. And if you somehow dig a bit or look at this a bit more closer, then it turns out that there are basically a good and a bad answer to this. And the bad answer I want to start first with. So the bad answer is that we don't really have efficient logarithmic lattice-based proof systems inside. So logarithmic here means that the proof size is logarithmic in say, the witness size. So in the case of our equation, basically the length of the vector that we want to prove. But the good thing is, and this is really basically new, that there has been a lot of progress on efficient linear proof systems in the last months or in the last year, and even so much progress that we can actually beat PCP type proof systems now for statement sizes that we encounter in actually interesting cryptographic constructions based on lattice assumptions. Okay, so Vadim has given 2 examples. Let me just repeat them. So what we are now able to do is we can prove knowledge of a 32-bit integer in, so Vadim said something like 7 kilobytes. I think it's more like maybe 5.6 kilobytes. And for these equations that we need for underlying lattice-based schemes, we can prove knowledge of a solution of basically, say, 2048 unknowns, modulo prime, which is 32-bit large in less than 50 kilobytes. So this is literally basically the problem, as Vadim has said, that you need to solve if you want to prove an LWE sample. So basically the takeaway message here is that there is a regime of problems where linear systems can be interesting. And we also, I think Vadim has also said this, but just let me repeat this. It's also not just important to somehow compare proof size, but what is also, of course, interesting in practice is the runtime of these algorithms. And it turns out that with lattice-based systems, we are basically far ahead in runtime than what can be done with these generic constructions. So even if our constructions are maybe slightly worse in terms of proof size, then we will still be able to beat PCP-type systems based on runtime. So maybe to make this a bit more concrete, there have been papers which have studied how to basically solve these linear equations over ZQ with, for example, Aurora, and somewhere. They have basically found that the runtimes of the prover of these implementations, they're in the order of several tens of seconds. And we are pretty sure that with lattices, although we don't really have an implementation for exactly these problems, but somewhere extrapolating from signature schemes and encryption schemes, it's pretty clear that one can implement our proof systems with runtimes which are in the order of maybe a few milliseconds or even less. So there's really a large gap. Okay. So,
Gregor, so there is this work of Yuval, I think Dan Bonnet and others that they construct a lattice-based snark, right? Thought, in principle this should be easy, but I thought their goal was concrete efficiency. Do you know how it, do you know how this how it compares to the efficiency goal that you want in some sense?
So I'm not aware of that they have really concrete numbers like in size of kilobytes. So, and I would be surprised if their results are really small, like tens of kilobytes. But so basically, so our goal is to construct proof systems for which are linear, but which concretely have small proof sizes. And if one basically accepts this, that the system will be linear, then the next big problem that one faces is soundness. And the reason basically is that, in these proof systems, there will always be some challenges from the verifier, and basically all the problems we have, they are really easy to solve if we allow for challenges which come from the queue. So this then would result in a soundness error of 1/q, because usually by guessing the challenge, you can cheat. So if there's only q elements or only q challenges, then with probability 1/q, but that doesn't have the secret will still succeed. And somehow this is kind of contrary to what is nice about lattice cryptography, or the high speed we see in lattice cryptography, because one reason for the high speed in lattice cryptography actually is that we usually work with a small q. So for example, in the case of Kyber, so some encryption system that was submitted to NIST, their Q really is just basically 2 to the 12th large. And in our proof system, so basically our proof system serves for proving some underlying scheme. So if you want to prove something, in this case about Kyber, then we kind of are forced to also take the same cue. So this would basically, if we would do everything naively, as is basically known how to do it, then this would result in a scheme which needs to be repeated basically 10 times to get negligible soundness error. And it turns out that such a scheme wouldn't be really competitive anymore in terms of proof size. So Vadim has already said that signature schemes get around this problem by introducing polynomial challenges. So they work over some ring and then have the challenges which come from a polynomial. But as Vadim has already explained, and I will say this again quickly, this is not so easy for proving things about commitment schemes. So therefore, some of the techniques I'm going to introduce, they're basically aiming at constructing protocols that achieve negligible soundness error without being basically simple repetitions of some base protocol with big soundness error. So this is only so to keep in mind, and this is, at least in my view, this is somewhat the biggest problem one has if one wants to construct really efficient practical lattice-based schemes or lattice-based zero knowledge, right? Yeah, proof systems. Okay, so with this introduction, I now start with some techniques, and basically the first thing we have to agree on is basically the ring in which we're doing arithmetic. And for this talk, I'm choosing such a power of 2 cyclotomic ring that Vadim has already introduced. And in our case, it actually turns out that choosing a fixed small cyclotomic like that one given on the slide of rank 128 turns out to be basically always enough, because you get yeah, basically a scheme which has secure parameter 128. So soundness 2 to the minus 128. Okay, so yeah, this is kind of already done by Vadim again, but I use a slightly different notation. So I say again what the commitment scheme is that we are working with, and maybe explain this a bit more in detail. So in a proof system, this usually works that you commit to the secret that you know. So in our case, this is some vector that fulfills some linear equation. And then in order to prove these product and unstructured linear relations that we are aiming at, you need to have a commitment scheme which is kind of sort of malleable, so that in the end, by applying, for example, certain homomorphisms, you get something which is 0, and then you prove that your message is 0, and by that you prove some linear relation. So I will explain this now. So, but just let me recall the commitment scheme. So in this commitment scheme that we are using, there's some public matrix B0, and then there are a couple of vectors B1, B2, and so on. And now you can actually commit to arbitrary polynomials from our ring, and you do this by sampling some short randomness vector R, and then you compute B0 times R. So this resulting T0, and this is basically for committing to the randomness. And then for committing to the messages, you compute scalar products of these vectors bi with the randomness vector plus the messages. And I will maybe slightly sloppily then say that, for example, T1 is a commitment to M1, although, of course, you also need this T0 so that the whole thing really is a commitment. Yeah, and yeah, as we have seen before, so this thing is hiding and binding, and the hiding comes from the fact that basically in every of these polynomials, there's some independent modular LWE sample, and the thing is binding because if you would be able to come up with a different opening with a different message, then you would also need to change the randomness vector, and this would lead to a modular cis solution for B0, so in the first equation. So, and what basically are the kind of operations we can perform. So there's basically we can do any, or we can apply any module homomorphism over RQ. So if we are given these two commitments T1 and T2 from the previous slide, what we can do is we can just linear combine them with two polynomials A1 and A2 from RQ. And then if we just plug in these expressions for T1 and T2 from the previous slide, just by some algebra, what we get is exactly of the form of a new commitment. So there's some new vector or matrix B3, which is just the linear combination of B1 and B2. And the message part is really the basically what we're interested in, namely the linear combination of M1 and M2. And this is useful because if we now have a tool to prove that T3 actually is a commitment to 0, then this applies some linear relation. So in this case, A1 times M1 plus A2 times M2 equals 0. Is there some question or no? Okay, so now we have our commitment scheme, and so I said what we need to basically be able to do is prove linear relations on the messages. And this first implies that we need to be able to prove knowledge of an opening for the commitment. Or I mean, of course, it doesn't make sense that we also need to prove that what claim with some commitment is really well formed and that we actually committed to something. And this works by giving this approximate proof of the first equation that Vadim has already explained. This is just this standard sigma protocol, which is modeled after Schnorr proofs. I'm not going into details here, just maybe to give the notation. So this masking vector y, which is sampled at the beginning, this I write this as a vector y, and then the challenge comes from some distribution big C, and in the end, the prover sends some vector z, which is y plus CR. And now to add this proof to that the message is 0, what we need to do is that the prover also has to compute B3y, and the verifier has to check some more equation. And so this is also important that this additional polynomial x doesn't have to be sent in the non-interactive part, because this can then be checked as basically input to the hash function, which is used for the challenge polynomial. So in practice, this means proving any linear relation over our ring RQ is as cheap as just proving knowledge of an opening of the commitment. And no matter how many basically relations we prove, which is very useful. Okay, so in the opening proof, what we get is not really what we might want to get. So we don't really prove the pre-image of T0, but of basically T0 times some small polynomial C bar. And the reason is, as Vadim has explained, that in the extraction, we try to get two accepting transcripts, and we call the difference of the two challenges C bar, and then by basically subtracting the verification equation, we get the equation which is written there, and it doesn't really make sense to divide by C bar, because dividing by some small polynomial will lead in something big, which is not really interesting for this equation. So all we do prove is that we know a short pre-image to T0. And of course, I mean, the honest prover knows this. He can just multiply his R by C bar, but what we can extract from the proof is actually much longer than what the honest prover knows. And this is why this proof is called approximate. Now, for signatures, this is enough and all we need to do. But now I come to the part why polynomial challenges alone in zero knowledge proofs of a commitment are not really enough. And as Vadim has already said, this is this problem with the invertibility of C bar. So kind of intuitively, the reason is that we also have to multiply all the other equations, so all the polynomials that actually commit to something by C bar, and then we don't really end up proving that the message we are interested in is 0, but we prove that the message times C bar is 0. And this is only really sufficient if C bar is invertible. Otherwise, yeah, we don't know. And we look at this a bit more detail. So recall that the ring we work with, so this cyclotomic of rank 128, this is splits into a product of smaller fields. And for this talk, I'm basically assuming that Q is some prime in, say, the order of 2 to the 32, and it is such that the ring actually splits completely. So this means that modulo Q, there is some 256 primitive root of unity, and then the factors of this irreducible polynomial x to the 128 plus 1 over z, yeah, these are these linear factors x minus ri, where ri are all the 256 root of unity. Yeah, and if I go back to this equation, so if C bar is not invertible, this essentially means that in one of these factors, and let's call them yeah, basically the NTT factors, or basically in one of the NTT coefficients of C bar will be 0. Because otherwise, if C bar would have NTT coefficients which are all non-zero, then C bar would be invertible, and the equation above would give what we want. But if C bar is 0 in one of the basically NTT slots, then there we don't learn anything, because we multiply something that we want to prove by 0, and then of course this is trivially 0. Okay, so what can be done about this? I mean, the usual strategy that has been used before is to just choose the set the challenges come from in such a way that just every difference of two elements is invertible. And then we don't have this problem, because we know that C bar is invertible, and there have been several techniques explained in the literature, and Vadim has explained this a bit more in detail, how one can construct such sets. But basically this always has in common that there cannot be a large challenge set unless Q doesn't really split much. And one can also very easily see this from a counting argument. So if you assume that as we do, our ring splits completely, then all these fields the NTT coefficients live in, they are just Q large, so their size is just Q. So if you have a challenge set which is bigger than Q, then there must be a collision. So there is a difference of two challenge which is 0 in this NTT slot. So it's clear that such sets cannot exist in our case. And what we now do differently is that we basically observe that non-invertible C bar are not useless. So Vadim hasn't really explained this, so let me spend a bit more time on this. So if we look at this equation before, then yeah, it is not completely useless, because it actually does prove the relation we're interested in all the NTT slots where C bar is non-zero. So one possible strategy can be that we just somehow try to set up our proof in such a way that you can get many transcript pairs with many different differences of the challenges, such that modulo every of these degree 1 polynomials, x minus rj, one of the C bar j's is non-zero. So concretely, so we really want to have as many transcript pairs in the extraction as we have NTT coefficients, and then basically the jth C bar is non-zero modulo x to the minus r, x minus rj. And yeah. So, and if then we basically can piece together all our extraction, and they give what we want, because from the jth extraction, we learn that the relation we are interested in holds modulo the jth degree 1 polynomial, and all together they prove what we want. Okay, so this could already lead to some solution to our problem, but we need one more ingredient for basically to make this really efficient. And for this, we have to look at the prime splitting or the splitting of our ring in a bit more detail. And what we see is that, or what is basically well known, is that this ring doesn't immediately split into these linear rank 1 factors, but it actually splits recursively in rings modulo polynomials, which are of a very nice form, so which are all monomials. And in particular, basically, it splits into some polynomial of degree 4, or yeah, so our cyclotomic polynomial splits into some polynomial of degree 4, which also is binomial, so which is of the form x to the 4 minus, in this case, r1 to the 4. And this is also really at the heart of why NTT algorithms are so fast, because you have this divide and conquer way of splitting a ring successively into more and more factors until you reach the NTT coefficients. For us, we now need also some automorphisms for our ring, and it turns out that our ring RQ actually has a group of automorphisms, which we might call out of RQ. And these automorphisms, they act very nicely on these factors of RQ. And in particular, by this, I mean that there is some cyclic subgroup, and let's say this subgroup is generated by some automorphism sigma that stabilizes every of these rank 4, basically subrings. And in addition, rotates the factors dividing it. So to explain this a bit more clearly, I have some graphics here. So let's assume we start with some polynomial C. So in the end, we will be interested in challenges. So this is why I call this C. And then if we look at the image of C in this rank 4 ring that we basically encountered before going all the way down to the NTT factors, then there we basically get C mod x to the 4 minus r1 to the 4. And then if we go all the way down, we get the NTT coefficients of C. And let's call them C hat 1 to C hat 4. So the ones which lie under x to the 4 minus r1 to the 4. And if we now apply our automorphism, so that generates the cyclic subgroup, which I said acts nicely. So first, I didn't really apply it. I just wrote sigma 0 so that I still have the same as before. But now if I apply sigma once, then what you see is that in the top, you now have the polynomial sigma 1 of C. So this is really just sigma applied to C. Then in this rank 4 ring, you of course also have then sigma 1 C mod x to the 4 minus r1 to the 4. And now the interesting thing is that the NTT factors are basically, or the NTT coefficients are the same as before, they're just rotated. So before we started with C1 and then had 2, 3, and 4, and now we start with 4. And if I now apply sigma a couple of more times, I see that I basically just rotate these NTT factors. And this will be very useful because this allows us to set up our proof so that in the extraction, we can get challenges C bar, which are non-zero modulo this degree 4 polynomial. So suppose somewhat that our proof that we will somehow look at in a minute, that this allows for getting an extraction where C bar is non-zero mod x to the 4 minus r1 to the 4. Then this of course means that C bar must be non-zero in one of the basically rank 1 factors which lie under this rank 4 factor, because otherwise C bar would be 0 in the rank 4 factor. And now because we have these automorphisms which rotate the NTT coefficients, this means that actually for every of the rank 1 factors, there will be one rotation of C bar which is non-zero in this particular factor. Put differently, so C bar basically, we start off with assuming that C bar doesn't have all the 4 entity coefficients under or in this group of 4 non-zero, and then by rotating them, we can basically get a polynomial which has a non-zero in one of the entity slots of our choice. And
Gregor, you have a question about polynomial splitting? You can read it. You want me to read it?
Wait, I have to move this, otherwise I cannot read it. Okay.
Do you want me to read it?
Vadim, maybe that's not a bad idea to read out the question.
Okay, sure. Well, it's fairly technical. So the question about, I guess it's about your automorphisms you were talking about is, doesn't this hold whenever the prime splits completely? We don't need it to split to linears, but just need the ramification indices to be equal. The Galois group would just permute these prime ideals, right?
Sure, yeah. I don't really get what the question is heading at. So whenever the prime splits completely, yeah, this is basically what I said, right? So I mean, maybe yeah. So the fact that the prime splits completely is precisely what maybe I understand what the question is asking. So maybe it doesn't split in this nice binomial way. Is this what the question is asking for? So because splitting completely means that it splits into prime ideals which have degree 1, which is exactly the situation I was looking at. Yeah, I'm asking, do we need the ideal P to split into linears? Yeah, this is what I'm assuming, yes. Yeah. Does this answer the question?
I think the question was, do you really need it to split completely? And I think the answer is no. I mean, this you can apply automorphisms also. If it doesn't split completely, you just have less of them.
Sure, yeah. So, so for example, so if we would not split completely, but say in only ideals or prime ideals of degree 4, then basically this group of automorphisms, this cyclic group that I was looking at, this would just be some automorphism on this on this field. But as basically for reasons that will be useful, and as Vadim has explained later, for our purposes, we do want our ring to split completely because it is useful in later protocols.
I mean, if it doesn't split completely, you don't need the automorphisms. You already have your
right.
your invertibility.
Right. Yeah.
Right.
Yeah.
So this is only interesting if it splits and you don't have the invertibility, I guess, right?
Right. Yeah. So the reason is, yeah. So yeah, maybe if yeah. So I explained that what we do need in the end is that we can extract a C bar, so a challenge difference, which is non-zero in all the basically in all the prime fields. So in all the entity coefficients, if we want to call them like this. And now if our ring doesn't split completely, then already by this assumption that I made on the previous slide, that C bar mod x to the 4 minus R1 would give us this situation. And then having such an extraction would prove something useful modulo this polynomial. But in our case, I do assume that the ring splits further, or the prime splits further. And so we do need extractions for all of the prime ideals. So we do need, in the end, a C bar modulo all of these linear factors, x minus R. And we achieve this by just assuming we can get some C bar, which is modulo, which is non-zero modulo some degree 4 polynomial, and then there will be some of the rotations which is non-zero in the modulo of the linear factors, or basically modulo the prime ideals. Yeah, so I hope this is now a bit clearer. So from a now I cannot close this window. Okay. Yeah. No. So from a protocol point of view, what we now do is just we repeat our protocol, the basic opening protocol 4 times, and yeah, basically sample 4 masking polynomials or masking vectors yj, where each yj is there to mask the randomness times the rotation of C with sigma to the j. So it's kind of a repetition of the previous protocol, but instead of completely independent challenges, we have one global challenge, and in the repetitions, then we use the permutation of this global challenge. And yeah, now you might ask, why are we doing this? And the reason is basically twofold. So first, it turns out that sending these zj, which are maskings of R times these rotations of C, this is going to be cheaper than sending basically maskings with challenges which are completely independent. This is maybe the smaller reason, and really the big reason is that it turns out that in the product and linear proofs that I'm heading at, that there this additional structure that we have on the challenges allows for protocols which don't have to be repeated at all. So you remember that in the beginning I said soundness is really somewhat the big problem to get to small concrete sizes. Now I was repeating basically some protocol just 4 times with 4 times the size. So you might wonder why I was saying in the beginning that repetition is bad, but it turns out that only this opening proof kind of has to be repeated 4 times, and all the other things I'm going to prove because of the structure I have now, I don't have to repeat. And we will see this in detail later. Is there some more question now? Or?
Yeah, this is Chris. I had the question for the first bullet, why is it cheaper?
Yeah, this basically means you don't, yeah, I was cheating a bit here. So what you really will send in the protocol is not the Z as I've written there, but what you will basically decompose C in, or write C over this subring of rank 4. And then multiplying R with basically with these coefficients in the basis of your full ring over this subring leads to a smaller basically C times R, and then you just mask these polynomials, and the verifier can then recombine them to get all the basically the maskings he's interested in with with the rotations of C. But yeah, I haven't really explained this.
Thanks, though. Yeah, I see what you mean now.
Yeah. Okay, so now the big question is, so I just gave this protocol and I said, what we try to do is we try to be able to get an extraction for every of these rank or degree 4 polynomials, which has non-zero challenge difference there. And how do we do this? This is basically what Vadim has said, but maybe now a bit more concretely. So the verifier will sample the challenge polynomial from some ternary distribution, and in such a way that all the coefficients, so let's call them C0 to CD-1, they will be basically independent sampled from some distribution over -101. And then we see that we can rewrite our polynomial by just grouping together coefficients which are basically 4 apart. So this basically means, as kind of what I said before, we write C in the standard basis over our rank 4 subring. And now by writing C in this form, you see that if I reduce C modulo x to the 4 minus, say, r to the 4, then what I do is just I evaluate these 4 polynomials at r to the 4 to get the coefficients of this basically degree 3 polynomial that I get by reducing modulo this degree 4 polynomial. And since all these polynomials, they involve disjoint sets of polynomials of our original C, the it's obvious that these coefficients, they will be completely independent. So if we just analyze the distribution of one of these coefficients, then one can, for example, prove that slightly informal, because it's now, of course, depends on the parameters and so on, but you can set parameters in such a way that the coefficients of C mod x to the 4 minus R4, so these relations of the polynomials before, that they have maximum probability over ZQ, which is really close to 1 over Q. So yeah, essentially they will be uniform. And since I said before, our Q is basically in the order of 2 to the 32, our coefficients will have maximum probability, which is essentially 2 to the minus 32. So why can I get now the extractions that I want? And intuitively, the reason for this is that if some prover would want to cheat, so he would never answer, you basically would pick one or you would only answer polynomials which have a particular value modulo x to the 4 minus r to the 4, then his success probability would be basically at most 2 to the minus 128. Because the best thing he could do is he could hope that the polynomial c that he sees is the one where all the coefficients have maximum probability, but they all have maximum probability, which is basically 2 to the minus 32. So that he gets this degree 3 polynomial has probability essentially 2 to the minus 128. Now, of course, we need extractions C bar, which are non-zero modulo all these rank 4 or degree 4 polynomials that appear, and these C's will not be independent modulo the different degree 4 polynomials, but we don't really need this because we are fine with having different basically extractions. So what we can do in the rewinding is we basically just run the prover until we get a first successful transcript. So the first challenge. And then for every of these degree 4 polynomials, we rewind the prover and send fresh challenges which just differ modulo this degree 4 polynomial until we get basically a second successful hit, which is then different from the first modulo this polynomial. And in this way, we can really get one transcript pair with non-zero challenge difference modulo all these degree 4 polynomials. And this is what we need then to also have, because we always then have prover replies of basically for all of these C bars, we have 4 prover replies, and there will always be one for every of the NGT factors, which is non-zero. And then we can piece everything together to get basically complete solutions as we want them. Okay, so then there's one more thing in the extraction argument, which turns out to be really nice in later applications. So I'm going to also explain this briefly now. So it actually turns out that a prover which has sufficiently high success probability so that we can extract something useful, basically always has to answer or has to send Zs which are of a very particular form. Namely, it is really of this form Y, or basically the Z J in the transcripts, they will be always of the form Yj plus sigma J C times R for basically constant Yj R that we can extract. So yeah, maybe a bit sloppy here. So what I mean, so maybe, yeah, so either you have, yeah, so what I have to restrict to here is that the prover basically always sends the same commitment in the first flow, which you can also, of course, achieve by just always just rewinding to just after the first flow. And not just are the Zj always of this form with constant Yj and R, but really the R is the randomness in the commitments. So we then also know that all these Ti commitments, they are really precisely of the form BIR plus MI. And this turns out to be a really useful tool because it makes writing soundness proofs for protocols which are based on this opening proof much simpler, because you now have these precise expressions for the prover replies and for the commitments, and then you can just plug them into your verification equations and don't have to handle challenge differences, and you don't have to subtract verification equations like one did previously. So it turns out to be much easier to work with this. And this result is also kind of, at least in my view, kind of surprising, because we don't, so for a fixed J, we don't have a non-zero challenge. But let's put it differently. So the Zj, there's a Yj which always masks the same rotation of C. So this sigma j of C. And for this basically fixed rotation of C bar, we don't have basically a transcript which is non-zero modulo all the entity factors. And still, we can somehow uniquely compute this Vj, and all the prover replies always have to be consistent. Also, with this Yj everywhere, which is kind of surprising. And in practice, this gives us a nice additional tool, because we can really use these Yj to commit to additional messages. So in these proofs, there's sometimes auxiliary information that we need to commit to, and it's kind of annoying to need to increase the randomness of the original commitment scheme just to basically be able to commit to additional messages. And now we can just use these Yjs that we have anyhow in our opening proof to commit to new things, which is useful. Okay, so yeah, maybe there's a good point now to ask if there's any questions. Okay, so because now I have all the techniques to really start with the product and the linear proof that we are eventually heading at. Okay, so yeah, to start with this, our goal now really is to prove this linear equation AS equals U mod Q with a ternary vector S. And now, so we now have our commitment scheme. We can prove openings about it in basically efficient way with these automorphisms that we don't really know yet why they're useful. But before we now come to the equation, what we need to somehow settle with is how do we actually commit to our vector S that we're interested in. And as Vadim has said, there's basically two ways how, two natural ways how to do this. So either you can use directly the coefficients of the polynomials we commit to encode the coefficients of S, or you can encode the coefficients of the secret vector in the entity basis. And in previous protocols, always a problem was that one of these encoding is good for one thing and the other is good for another thing. So in particular, encoding secret coefficients in the basically in the coefficient basis is very good for this linear part of our equation that we need to prove. And yeah, especially if the equation we look at is actually an equation over our ring, because then, as we have seen, this is completely trivial with the commitment scheme we are using it. And for practical purposes, this would probably be even enough, because we could always work with ring-based underlying schemes that we want to prove things about it. But in this representation, we don't really know how to prove shortness really efficiently. And as Vadim has explained, this can be done efficiently if we encode in the entity basis. But then the linear proof gets difficult. So since the range proof somewhat seems to be more difficult, what we do is we decide to use the entity basis to commit to the coefficients. And then we have to say how we can actually do an efficient linear proof in this basis. Okay, so now first for the range proof, this we have also seen before. So basically range proofs are always based on the observation that something is in -1, 0, 1, if and only if it is a solution to this equation S times 1 minus S times 1 plus S. And now if our commitments are really such that the entity coefficients of our polynomials are the secret ternary coefficients that we're looking at, then multiplying m as basically polynomials with 1 minus m and 1 plus m gives this component, gives basically all these interesting products in all the entity slots. So we get this pointwise product of the S vector with the one which is basically 1 minus the vector, and then the one which is always 1 plus the vector. And if we are able to prove that this is 0, then we have actually proven that all the coefficients are ternary. So this is why we want to use this entity representation, and it also shows why we want to do a product proof. So what I'm now extracting from here is that we need to be able to prove products, and that they can be polynomial products, because basically polynomial products show what we are interested in the entity representation. So now there's kind of a general principle of how to do such product proofs, and the general thing that you always kind of have is that somehow the verifier, and the simplest case of course is that the prover just senses, the verifier needs to have some mask opening of the things you want to that you want to multiply. So in our case, mask openings of these two polynomials m1 and m2 that we want to multiply, and are now use basically the same letters y as before for masking terms, but these are different masking polynomials than in the opening proof. I just don't want to introduce new notation now. So if we do this, if the prover sends two mask openings of m1 and m2 with some challenge polynomial c, then the verifier can just multiply these two mask openings, and then he gets a new mask opening of the product. So more precisely, this means that if you just multiply f1 and f2, then we get some quadratic polynomial in C, where the constant coefficient is just the product of the two maskings. Then we have some linear term which consists of kind of two cross terms, so y1 times m2 and y2 times m1, and then in the leading term, so the one which is quadratic in C, there's actually the product we're interested in. And this can be turned into proof of a product relation by letting the prover commit to these two boring terms, which are in the linear and in the constant part. So let's call these polynomials just G0 and G1. So the prover commits to these two polynomials, and then gives a proof that this product of these two mask openings is equal to G0 plus G1C plus M3C squared. So yeah, so he has a commitment to M3. He can just multiply this by C squared, and then multiply his commitment of G1 by C, and add all of this with G0, and prove that this is equal to F1, F2, which he has. And if one does this, then this proves that M1 times M2 is equal to M3, but only with soundness error 2 over Q in this case. And the reason is that although our challenge polynomial now can be completely uniform in our ring, it is still basically the case that in each entity coefficient, the prover can cheat by hoping for a C which makes this quadratic equation true, although M1 times M2 is not M3 in this entity coefficient. So basically, if M1 times M2 is not equal to M3 in one of the entity coefficients, you can still set up the proof so that for two challenges which make this quadratic equation true, or basically challenges which have two values in this entity coefficient, he still gets basically achieves, or yeah, gets an accepting proof. So this is why this has soundness error 2 over Q. Other than the soundness error, there's two more problems with this approach, and they are even more severe. So the first is sending these mask openings Fi is really expensive, because they are basically uniform polynomials that have to be sent. And in order to prove that these F are actually really maskings of the messages, you also need to then commit to the masking terms and prove that the F are well formed. Otherwise, the prover could just send some arbitrary polynomials which don't have anything to do with the M's. And yeah, this of course wouldn't make sense. And now I said this protocol only has soundness 2/q, so you need to repeat it a couple of times, and then you cannot basically use the same masking terms Y to mask M with different challenges. Otherwise, this would break zero knowledge. So if you repeat, you would need additional commitments to Y, and so there's a huge amplification of things that you need to send in order to use this approach. So what we are now doing differently is that from our opening proof, we have this very nice basically formulas for the prover replies and the commitments. So we do know that these Zj, they are precisely of this form Yj plus sigma jc times r in all accepting transcripts. For basically for all C's that the prover replies and gets an accepting transcript, the set J is of this form, and the commitments also have this equation which is given there. So if I know this, I can compute the following terms. So I can just take this commitment vector BI, so for the ith message, multiply it with a Cj and subtract sigma j of C times Ti. And if I plug in now the expressions that I know in the extraction, then I see that in both of these terms, there's one equal term which cancels, and namely there's so in this scalar product there's one term which is essentially b times cr, and this also appears in the other term because the commitment contains this b times r, and if I multiply by something which is essentially c, then I also get this b times c times r. So this term cancels out, and what remains in the scalar product is just this b times y term, and from the commitment what remains is just the message times our challenge. And if we look at this now, then we see this is really nothing else than a mask opening of our message. So what this means is there's really no need to send these mask openings. We can just let the verifier compute them himself, and then we save a lot on communication and committing to masking polynomials and so on. So yeah, this doesn't have communication cost, and basically the well-formedness of the mask openings is follows by construction. And then the proof is kind of finished by the same verification equation that basically I explained before, but now we have these 4 repetitions of our protocol with these 4 rotations of the challenges, and for each of them we have a mask opening, so we kind of have 4 quadratic equations that we can compute. So yeah, so basically for each message we have 4 mask openings for all the 4 rotations of the challenge. We can multiply 2 of them, then subtract the corresponding mask opening of the 3rd message, also with the same challenge, and then prove that this is equal to 2 garbage terms. Yeah, and this. Yeah, okay. So I hope this is clear. So if we would do this, we would need to basically, for all of these 4 repetitions, we would need to commit to 2 garbage terms. So we have 4 j's, and in this equation, there's basically 2 g's for every j. So in total, we would have 8 garbage terms. And now, basically, we see the first instance of why our automorphisms are useful, because if we look at these mask openings from a slightly different point of view and apply sigma minus j to basically to the opening of the ith message with a jth automorphism, then what we get is a mask opening with just basically the bare challenge C, but with a rotated message. It's just of how automorphisms work. And we can linear combine all these mask openings, and then we get some quadratic polynomial where in the leading coefficient we actually have a linear combination of all the rotations of our message. So I don't know if this was too fast. Yeah. So maybe I'll just say the last sentence again. So what we are able to compute is basically some quadratic equation as before, where in the leading coefficient we now have a linear combination of the rotation of the basically of the relation we are interested in. And this is very useful because if we now analyze the cheating probability of the prover, then we see this, if we prove that this is 0, then this already proves really the full relation with negligible soundness error. And the reason is the following. So if we assume that the relation is not true, so suppose M1, M2 is not equal to M3, then I mean, without loss of generality, this means it is not, so M1 times M2 minus M3 is not 0 modulo 1 of these linear factors. But then in this linear combination that I had on the previous slide, I basically rotate this non-zero term to all the other entity coefficients and multiply it with a completely uniform factor which comes from the verifier. So these alpha j, they are challenges from the verifier. So this means that in this linear combination, I get something which is completely uniform in our rank 4 ring, although we only basically assume that it is maybe non-zero in only one of the entity coefficients. So basically this non-zero thing gets spread out in all the 4 factors which below one of the degree 4 polynomials. And the prover can only cheat in at most 3 of them, because otherwise his challenge difference would be 0 in the full rank 4 subring, and therefore this really proves basically the relation we're interested in with negligible soundness, or soundness 2 to the minus 128. Okay, so now, to wrap this up, so what we have seen is that these repetitions of the opening proof with automorphic challenges or images of the challenge under automorphisms allows us to get an opening proof which isn't really any repetition of some basic protocol anymore, because we still only have 2 garbage terms, so one can even do it with only 1 garbage term that we need to commit to. Okay, so this kind of finishes the product proof. Are there any questions? Okay, so if not, I can continue. So then, or we can also maybe do some break, I don't know.
I think you have 20 minutes left, so just go on, I guess.
Okay. Okay, so now I hope I have kind of explained how the product proof works. What remains is that we need to be able to prove linear equations over our entity representation. And so recall that we committed to vectors in the entity basis, and we want to prove linear relations among these entity coefficients. And there, basically, the key observation we need is, as I've said before, so the polynomial product is component-wise in the entity basis. And then we need a second observation, and this is that the constant polynomial coefficient is actually the sum over the entity coefficients. And this is something which is easily seen if one looks at how the entity algorithm works, or in this case, the inverse entity algorithm. So this means together, these 2 things give us a scalar product, because we can multiply and then we get products of all, basically in the individual components. And then if we look at the constant coefficient, we get the sum over all of these. So to make this a bit more precise, I assume that we have our message polynomial M, whose entity is the secret vector we're interested in, and then we have some other polynomial a, which in the entity has some vector a. And if we now take the product of these polynomials a and m over the ring and look what this means in the entity, then of course this is just the component-wise product. So we multiply a1 by s1 and a2 by s2 and so on. And then if we look at what this means for the constant coefficient of the polynomial am, so then the map we have to apply is basically the inverse entity and then the map which gives us the constant coefficient. And because this is just the sum over all the entity coefficients, we see that this is the sum over these products a, y, si. So this is nothing else than the scalar product of a times s. So with this observation, we basically have a tool to prove scalar products. And this is all we need, because as soon as we can prove scalar products, and what we can do is we prove that, as minus u times some challenge vector gamma is 0 as a scalar product. And because this proves that a is equals to u with a soundness error 1 over q. So I hope this is clear. I mean, if a is u, then a is minus u is 0. So the scalar product is trivially 0 for all challenges. And otherwise, we have some non-zero polynomial, which we take a scalar product with as some uniformly random challenge vector. So this will be just some uniformly random element in ZQ. And in particular, 0 only with probability 1 over q. Okay, so in order to implement this plan, what we need as basically for our commitment scheme is that if we have a commitment which is somehow computed in such a way that we know that the constant coefficient is some scalar product that we're interested in, then we need to prove something about this constant coefficient. In our case, we need to be able to prove that the constant coefficient is 0. So so more precisely, we have this polynomial m, which in the entity has this vector s. We multiply this by the polynomial, which is at, so the transpose of a times gamma in the entity, and then we subtract u times gamma as scalar product. And as I explained before, what we get is a commitment to a polynomial whose constant coefficient is the scalar product. So we need to be able that the constant proves, we need to be able that the constant coefficient is 0. And this works in the following way. So what we let the prover do is we let them commit to some, let's call it a masking polynomial g, before he sees the challenge gamma. So he commits to some polynomial g, which is 0 in the constant coefficient. And then after he has seen gamma, the prover can send g plus f. And this is useful because if our relation is not true, then we know that the constant coefficient of f, so f0 is some uniformly random element. And then this something g, which is independent of gamma, because g was basically committed to before the prover saw gamma, then also in this sum, the constant coefficient will just be random. And otherwise, if f0 really is 0, then f plus g will also have constant coefficient 0, because we just, in the constant term, we just add two zeros. So this is how this works. The prover commits to g and then sends g plus f after seeing gamma, and the verifier checks that this g plus f is correctly computed and that the constant coefficient is 0. Now, again, we need to somehow boost soundness, because as I've explained, proving one scalar product only gives us soundness 1 over q. So we need to prove basically 4 scalar products which all have random, or independently random challenges. And then if all of them are 0, then we really have proven our linear relation with negligible soundness error. So how do we do this? So let's assume we have 4 polynomials f, where the constant coefficient always is such a scalar product with some independent challenge. Then what we kind of want to do is we want to add them together in kind of a shifted way, so that we get a polynomial which has four interesting coefficients in a sense. And we do this by first mapping these f down to the subring where basically by construction every fourth coefficient is 0. So this works by applying the trace map, and it turns out that this trace map is just given by the sum of the automorphisms we have. So this is really nice because this is something we can compute. And in particular, TF now lies in this subring. So by construction, every fourth coefficient, only every fourth coefficient is non-zero. And the constant coefficient still is the scalar product we're interested in, because this trace mark kind of preserves the constant coefficient up to scaling. So it just gets the constant coefficient from before, but times 4. So now if we define this following new polynomial f, which we just compose of this trace of our fi, but always shifted by 1. So we add all the rotations of f and always multiply by x to the I. Then we get some polynomial where the constant coefficient is the constant coefficient of f0. So this is some interesting scalar product. There's no part from the other basically traces or images under the trace of the other polynomials, because if we rotate them, then the constant coefficient will be 0 by construction. And then in the second coefficient, we get a second scalar product and so on. So what we just need to prove is that the first 4 coefficients of our polynomial are 0. And I hope it is kind of clear how we can do this with the approach before. So this masking polynomial g that we had is now just a polynomial which has 4 0 coefficient in the beginning. Okay, so this is basically all I wanted to explain. Yeah, are there any questions?
Thank you for a great talk. Shall we thank the speaker?
It's very dark here. Do you still see me? I don't see myself. But... okay, no.
We see you.
Okay, so it has, yeah, it's already 9 o'clock, I think. Yeah. So.
Vadim, you are muted, I think. And
yeah, I wasn't saying anything interesting. So
okay.
All right. Thank you.
So I think this ends the first day. Is that correct?
Yeah.
And we'll see each other tomorrow at 8:30.
Okay. Bye.
Okay.
Tomorrow.
Have a great day. Bye.